Thank you very much, as I have said, for joining the second Edgeless Info Day. We are very happy that you are here, and I hope that you will enjoy the different sessions that we have prepared for you. Okay. This is the agenda for today. It's essentially divided in two sections. In the first section, we will be talking and explaining to you the different developments that we've been doing in the Edgeless project. While in the second session, we will have 5 different very interesting talks around the different developments in the Edge Cloud Continuum that are completely complementary to what we have been doing in Edgeless. So I hope that you will enjoy all these presentations. To start with, I will just give a very quick overview on the Edgeless project. Probably if you have attended previous sessions, you will already know, so I will go very quickly. And then after that, we will proceed with all the different presentations. Just to start, just to remember that, let's say the main goal of Edgeless is to optimize the Edge Cloud Continuum. And unlike other approaches or other solutions which are more based on the vertical offloading of resources, in which the edge maybe is essentially supplementary to what the cloud is providing, in Edgeless we have focused on the horizontal pooling of resources among the edge nodes. This allows us to work with edge nodes with different capabilities, at the same time that we have fully integrated with cloud resources. We can also summarize this with this short sentence, which we call the project ambition, the low-code development of IoT applications to be deployed and managed in an efficient and secure manner in the Edge Cloud Continuum. In the next presentation, we are going to have a lot of detail in what exactly this means. Now, I only want to mention that when we are talking here about applications, of course, Edgeless is applicable to many different kinds of applications, but in particularly inside the project, we have developed 3 specific use cases. These use cases are the advanced smart city surveillance, the Internet of Robotic Things, and the healthcare assistance. In the next presentations, we will provide you with a lot of details in these use cases. We will be even showing you several demonstrations on these use cases, so you will get a lot of details on this. And just to finalize, I just want to remember the Edgeless Consortium is a mix of large enterprises, small enterprises, universities, and research centers that we have been working together during 3 years. We are at the very end of the project, and we have been able to deploy what we are going to show during today. So nothing else from my side. Next presentation is from Claudio Cicconetti, our technical coordinator. So Claudio, the floor is yours.
Thank you very much, Tony. I will share the slides immediately and then get back to action. I will provide a scientific and technical view, which will be quite short. So like Tony said, I invite you to check our online resources for more details, and I can assure you that there are a lot of them. So let's go back to the ambition, which is the central point of our project. So I will start from this. I will reread it again. We want to, we had achieved our ambition of realizing low-code development of IoT applications that are deployed and managed efficiently and in a secure manner in the edge cloud continuum. Now I will break down this ambition to explain pieces by pieces what we have done to achieve the full picture. Apologies for the noise, I don't know if you can hear it. So, first part, low code development. So in Edgeless, we have brought forward the model beyond function as a service. So as you know, function as a service can be seen as an evolution from the older cloud models, infrastructure as a service and platform as a service. In Edgeless, we went one step further because we wanted to have the function as a service programming model, which is nice and clean, and developers like it because you can compose also using low-code tools, visual tools, your application. But unlike the classical serverless computing, we also wanted our workers to keep a local state. Because a lot of applications, especially in the IoT world, which is of our interest, have applications where at least some of the functions have some local state associated with the user session or the user data in general. And retrieving the state back and forth puts a lot of burden on the network and on the use of external services, which we didn't want in the edge especially. So as tangible results, we have created a set of APIs which are open and available on GitHub with an annotation model that empowers the DevOps in providing a smart allocation of resources in that they control. We have provided software development kits in both Rust and Python to develop your own application together, possibly with the set of functions that are already shipped together with the Edgeless platform. So the IoT applications are those that Tony has already mentioned. We have identified the 3 use cases, and from then we have derived the requirements which have led to design choices that have been embedded since day 0 in the platform design. And one of the key choices we made is the use of lightweight execution runtimes. So while Docker containers, virtual machines, they are very convenient because they provide a strong isolation and they are widely adopted. We felt that, especially in the edge and especially with small devices with constrained resources, they could be too heavyweight. And in fact, as we have used WebAssembly as a lightweight virtualization abstraction, which allowed us to provide much better result by also maintaining the same level of quality and robustness in the overall architecture. And we have to interconnect with realistic applications. We have provided industry standard triggers and sinks that allow the edges functions to interact with the real world. Regarding the deployment and management of our applications, we have devised a DevOps cycle which allows to have the function development from the requirements to the code, and then a function repository which keeps the artifacts, the binary, the WebAssembly bytecode binaries of the functions when WebAssembly is used. And those can be deployed as edges workflows together with the annotations, allowing the application to run while telemetry metrics are collected both at a global level from all the domains that the cluster is made of, and at a local level in groups of nodes that are orchestrated together for better scalability. And all this telemetry data can be
okay, because this part we have some relationship with.
And all this telemetry data can be analyzed and then used to spin again the develops continuous cycle. As tangible results, in addition to reactive orchestration tools, we have also defined a set of best practices to be implemented for a realistic deployment. We have dealt with the efficiency and security by integrating with GPUs for the efficiency part, so that if an edge node or a cloud node has a GPU available, then it is possible to use efficiently those resources via different mechanisms, also making it possible to share the GPU across multiple applications. We have implemented a secure registration mechanism so that when a new node joins the cluster, the node this entry is authenticated by means of certificates, which can also be provided inside the hardware security modules, which make it very difficult for an attacker to forge, or even impossible. And it is possible for the execution of functions to run in a security enclave, such as Intel's SGX, so that you can really trust the function to perform the intended application logic, not something else that has been injected by an attacker. And in general, we have anomaly detection mechanisms that run at different levels in the system to assure a continuous and smooth operation. And finally, regarding the edge cloud continuum, we have from the beginning, we have designed Edgeless to be amenable to edge computing environments. And this means that we have decentralized the management, but at the same time, we have also considered the possibility for the cloud to be there, because of course, it's a very reliable reservoir of computation capabilities. And in fact, we have also developed a mechanism to activate on-demand nodes on edges nodes on AWS if the load on a domain exceeds some given thresholds, so that you can only use extra cloud resources when needed, when the edge resources are not sufficient due to some spike in the use of the resources themselves. We have a central function repository that keeps the artifacts, which was already mentioned, and we have ready to deploy images of all the core components of the systems that are automatically created when a new release is made on GitHub. And we have an integration with serverless computing platforms when this is relevant and useful, for instance, OpenFaaS. All this has a lot of complexity inside. Trust me, there are a lot of moving parts, and this picture, which I will not go into the details, shows the list of the components of Edgeless and how they interact with one another. Well, we have been able to manage the complexity by building on existing technology. So every single component was not done from scratch, with very few exceptions, but in many cases we have integrated and incorporated mature technology partially listed in the slide. And this also required a tight cooperation between all the partners. So as you can see in here, we have the same components with the partners who are mostly responsible for the development of that component. And we have a lot of interaction, which has been made possible by great teamwork that I must recognize in the project. Very quick highlights. So especially regarding this stateful function as a service pattern, This is just a glimpse of the many results we have obtained to fulfill our technical KPIs. So in here, I show a comparison between Edgeless and a possible competing technology, which is WASM Cloud, which is a reactive system also using WebAssembly, where, however, the functions are stateless, as they are in most serverless computing platforms. If you want to have a state inside a function, you have to use a persistence service external to it, such as Redis, which we used in these experiments. What we see here is that if we have different applications with bigger and bigger states, so the number 1,000, 100,000, 1 million is the size in bytes of the state of the function, and we increase the load over time by adding more and more users to the system. With Edgeless, the average load remains more or less stable, while with WASM Cloud there is a sharp increase in the load. You can note that the axis on the Y scale is different between the two plots, because WASM Cloud, in addition to performing the application logic, also has to access the state, which costs some CPU cycles. And most important, this creates an additional burden in terms of the latency. So the latency for Edgeless is always below 10 milliseconds, even with the biggest local state of functions, while with the biggest state in Swarm's cloud, the system becomes basically unstable. And when too many applications are present, the latency goes skyrocketing. To conclude, Edgeless will finish very soon, in 2 weeks. So what do we leave for the future? Well, we leave a bunch of deliverables and scientific publications, which are very interesting, and I invite you to check the list in our project website. But we also leave quite a lot of code. We have many repositories, and in particular, there is one core repository which contains the reference implementation of the key components of the system, which has been created almost immediately, and then it has been active throughout the lifetime of the project. So this is the screenshot from the GitHub on the contributions, and starting from summer 2023, the project started in January 2023. We have almost uniform, except for the August months, distribution of the contributions to the repository. So you are more than welcome to check it, and please get back to us if you want to be part of the Edgeless maintenance and user base. Thank you for your attention. Tony, do you want to get back the floor, or shall we
No,
move to the next
we can move
presenter?
directly to the next presentation from Bruno. I see that you are ready, Bruno.
Morning, everybody. I don't know if you can hear me and see my presentation, but I will assume so. Good morning. I'm Bruno from Ubiware, and we were part of the Edgeless project as a use case. Our use case for the smart city analytics. The use case consists of computer vision systems, surveillance, that leverages Edgeless orchestration and flexibility. This is because let's move forward. Our main goals were fast response, high availability and resilience, and that's very important, and data privacy. We used the use case was built on our infrastructure developed that we have as a test bed with edge nodes for testing. So just a quick. So this is our headquarters at Ubiware, and this is where we do all our tests. The infrastructure consists of smart lampposts with cameras, edge nodes, sensors. We also have a data center where we can deploy things. And this is where we deployed Edgeless and where we tested everything. So our workflow for Edgeless, we have a computer vision system that we had previously, and we decomposed this in several functions to be stateless, with the exception of one function, which is stateful, which is the tracking function, which is the function that defines if an object is already existing on the previous frame or not. And this is why it's important for us to use Edgeless in this situation, because this allows us fast keeping of the tracking and the state of the object. Very quickly, so our results were at the end of the project. So we were able to support multiple hardwares. We have also cloud and the data center that we use, and the edge nodes, which are Jetsons. We were able to keep an high availability by moving the workload, mostly edge to edge. That's our focus, but also edge to cloud on failure or on increased workloads. We kept real-time event detection. That's what we had previously and we wanted to keep, and that was demonstrated as well. We are able to send alerts when hazardous events occur, because one of the main goals of our application is to detect hazardous events like crashes or detect incidents that occur. And we focused on edge processing so we can ensure data privacy. The fact that we do most of our work on the edge means that we're not transmitting video feeds into the cloud. It makes it less likely to have issues with data privacy. So I have a very short video here, just to show mostly the orchestration and how we were deploying. So very quickly, I have a master node here where I start edgeless, and then I added two Jetsons to the system. I'm just gonna play the video here for a second. So I have Edgeless running. I will add the two edge nodes to the system, to the cluster. We can see here that just a second, that the system has three nodes on the cluster, which are the main one and the two edge nodes. And then I can deploy a workflow. A workflow is one camera that's associated with a smart lamppost. And in this case, because there's only one workload, Edgeless is going to distribute the workload by the available nodes on the cluster, which, as I add more workloads, it's important to keep the workload distributed and ensure that my inference times, the speed at which I detect objects, is kept low. And it also, we also tested to ensure the availability. So if one of the nodes dies for some reason or has a high workload, I want to make sure that whatever functions are running on that edge node are reconfigured to the available nodes as fast as possible, and that I don't lose much data. So we can see that the function that was running on Jetson 2 died, and it showed up pretty quickly. So the times that we're getting, it's under 20 seconds, and it's already started on another available node. This ensures that we are very resilient and that we can adjust workloads through our system. We tested this for multiple workflows at the same time, and the results are always really good. The limitations we have here and things that we've learned, since we are using a lot of heavy GPUs and we use things like PyTorch, we were a bit constrained to use containers, essentially, but some of the functions that we have are WebAssembly, but most of our work is still on containers, so it does not take into advantage the full Edgeless work. But we're very happy with the results that we're getting and the speed and the resilience that this work has gotten us. This is all my presentation, but I'm very happy to answer any questions that you have regarding the work that we did. So if there's any questions now or later, I'm very happy to discuss them.
Okay, thank you very much, Bruno. I think if there are no questions, maybe we can go to the next presentation. Eric, now the floor is yours.
Okay, thank you. So, Bruno, I need you to stop sharing a screen so I can share mine. I think now I will be able. Yeah, okay. You can see my screen, right?
Yes.
Yeah, nice. So, good morning, everyone. I'm Eric Domingo. I'm a researcher in the robotics unit in EURECAT. And during this presentation, I want to explain how we apply the Edgeless framework in the use case of Internet of Robotic Things. So just an introduction. I work with industrial robots, and this kind of robot have a recurring problem. So basically, the robots are very good at doing fast tasks and repetitive ones, but they struggle with cognition and heavy processing. So basically, they struggle in thinking. Nowadays, the modern applications require heavy AI processing because the robots need to understand the scenario, the environment, understand voice command, recognizing different objects, and be able to process all the hierarchy of the processes. And then, so one thing that we can accomplish all these things are putting high-end GPUs on every robot, but this is so expensive and it's energy inefficient. So with the Edgeless project, we have a way to offload these heavy tasks to remote computers. And I will show you now the work that we have done in this use case. So basically, we have combined both the robot controllers with Edgeless serverless architecture, having this way and speed architecture. We have a local machine that it's attached to the robot and manage the robot movements and safety, and we have the edge nodes that it's basically we use them basically for compute this heavy workloads. For our use case, we implemented 3 different functions. We need to identify, recognize speech to text. Then we need to detect different objects. And we need to reason all the plan-based and be recognized by the robot and do the different movements. And with this approach, basically the robot doesn't know.
Interrupting. If you are changing slides, we are still seeing the initial one. Okay.
Yeah.
Yeah, it's fine.
It's moving now?
Yes.
Okay. I don't know if you want to start again because I don't know what you saw.
I think you can go on.
Yes, I think that you can continue.
It was
Yeah.
easy to follow in
Yeah.
any
Okay,
case.
thank you. Yeah. So as I was explaining, for the use case, we implemented these 3 different serverless functions. We need to recognize some speech to text. Then we need to detect some objects on the robot workspace. And then we need to create the plan of the different actions the robot will need to do. And it doesn't matter whether the coder runs, because the robot will just send a request and the Edgeless orchestrator will do the rest. So I have here a video showing some demo, showing the demo of the use case. So basically, this scenario is done with one robot. We have 2 Jetsons, different sensors that are microphones, cameras, and the local machine running on the robot. And here the operator just says a command that they need to clean all the workspace and give some different tools. This is the process. Well, you can see here the different terminals where the code is running. So we have here locally running.
We
Yeah.
cannot see the video.
You
If you are
cannot-
playing the video, we are not seeing the video at the moment.
And having a lot of problems. Sorry about this. You see the video if I put it this one?
Yeah.
Okay. So the user says a voice command, I need a space on my workspace. Then this is how the system interprets it. I need to do some queries, and here you have all the different terminals. First, running in locally of the robot side, we start all the system. Then here we start the application here. Okay. And then after, it takes a bit, but then we can start now. And when the operator says the command and it's interpreted in the Edgeless side, you will see this first node that interprets the voice to text. Then the next one executes the YOLO that basically give the different objects on the workspace and the position. And this last one is the LLM that says the position of the objects where the robot needs to go to grasp them and the behavior to move them to the other side. So this is what the robot is seeing. With the YOLO, we can see that the different objects are detected and the different actions are also planned. So the robot can execute them, achieving the goal that the operator told at the beginning. So for this demo, the release area is the same for the both objects, well, for all the objects, but then we have another prompt. So basically, the operator can ask just for one piece, one object, and put it also in some defined area. So once again, after interpreting the text-to-speech, the is interpreting the objects and the positions and executing the LLM function for the robot. And then now the robot grasps just the hammer and moves to the position. Okay, so lessons learned about this use case. So at the end, we have some performance. We tested the system. We validated the latency, the throughput, and the stability of the system. We also have been able to offload heavy tasks of the robots and and in the edge, so the robots can take profit from them. And this way we can give the robots just the work to interfere with the safety and robot commands. And also doing this, applying this architecture, we don't need expensive GPUs on every robot cell. With a single edge server, we can serve multiple robots. And all this system has been very easy to integrate in multiple robots and system. And that's it for my side. So if you have any questions, same as Bruno, if you want to ask now or later, I will be welcome to answer them.
Okay, thank you very much, Eric. If there are no more questions, we can go to the next presentation, which is from Francisco Vicente from Worldline.
Okay. Can you see my screen?
Yes,
Yes.
but it's not full screen yet.
No?
Yes.
Okay, so I'm Fran from Borderline, and I'm going to present the healthcare assistant use case. I'm going to start this presentation talking about the senior care solution that we have in Borderline. This is a healthcare solution for caregivers and family members of senior people that allows them to monitor the activities and also the alerts or anomalies of these senior people at home. The idea is to gather information from several devices, and based on that information, based on that data, being able to detect activities and anomalies and act if necessary. Here you can see the dashboard of senior care in which the caregivers can monitor the activities and the alerts and take action if required. So I'm going to focus on how this senior care solution that we have in Borderline is taking advantage of the Edgeless functionalities. Well, the idea for this use case is to use a lot of sensors located in the homes of these elderly people. As you can see on the blueprint that is shown on this slide, we have a home with a lot of sensors located in different places in the different rooms of the home. Well, based on the information that is being generated by the different sensors, that data is triggering the Edgeless workflows, and the Edgeless workflows, by using AI models, are able to detect the activities and the anomalies of the people at home. On this slide, you can see the list of possible devices that we are using. We have MYRTUS devices, motion devices, smart plug devices, window door devices, and smoke devices. Well, there are two important considerations that you need to understand about all of these devices. The first one is that for this pilot, for this demo, we are not working with real people, with real homes, but with a simulator instead that emulates the behavior of all of these devices. The second important consideration is that most of these devices generate data only when a change of state happens, except the smart plug devices, which generates data every minute. It means that even if the person is not doing anything or is not at home, the system will be continuously generating data every minute, which means that the system will be, the sensors or the simulator that we are using will be triggering the execution of the Edgeless workflow every minute, no matter if the person is at home. And here you can see the Edgeless workflow that we have defined for the use case. Well, I must say that this is a simplified version of the Edgeless workflow that we have for the use case, because we are not including here several resources that we use for logging purposes and also to enter and exit the Edgeless workflow. But I'm going to explain this simplified version so you can understand what we've done. Everything starts from the bottom left in which we have the senior person simulator that emulates the behavior of these senior people at home by emulating the behavior of the different sensors that I have explained previously. So every time this simulator generates data, a sensor generates data, it triggers the execution of the Edgeless workflow, sending as an input the data generated by that sensor. And in the Edgeless workflow, we have all these functions. I'm going to focus on the main branch of the workflow, which starts with the data passing and formatting that evaluates and validates the data, adapting the format. Then we have several stages to prepare the data for the machine learning models that we have trained. Something important regarding these stages is that we have a manage state function. We are taking advantage of the stateful functions provided by Edgeless because in order to detect activities and anomalies, it is not enough having the last sensor data that has triggered the workflow, but we need to have all the previous sensors data within a time window that we have defined of 24 hours. So we need to use all the sensors data within the last 24 hours from all the sensors that are placed in the home. Therefore, we need to use these stateful functions, and we have a function to manage the state so that we always keep the last 24 hours. After these machine learning processing stages, what we have is the two anomaly detection and activity identification models. We have two models, one to detect anomalies, another one to identify activities. And these models will detect anomalies and identify activities, and after those, we have the interpretation of the results and format the data to be sent to the senior care system. Senior care can receive the information through a REST API and store the activities and anomalies that have been detected by the Edgeless workflow in a database. And then we have the front-end application of senior care that caregivers can use to monitor the activities and the anomalies and act if necessary. Regarding the infrastructure that we are using for this use case, well, we are working with one Edgeless cluster with a single orchestration domain, and in this orchestration domain we have the controlling and orchestration in a testbed. In addition to that, we have one node in the testbed and 3 nodes for 3 homes. In each of these nodes, which is a Raspberry Pi, each of them, we have the senior person simulator and one Edgeless node. And for the demo that I'm going to show you, we are able to identify all these activities, but the anomalies are not included in the demo because at the moment we are testing the anomalies because we just integrated that part in the workflow. So I'm going to show you the demo that we have recorded. Well, before playing the demo, I would like to explain that in this demo, I have opened a web browser on the right side, and on the left side, I have 2 terminals. The top left is open with the logs from an Edgeless node. So from time to time, you'll see that a lot of things are happening here from the logs of the different functions that we have in the workflow. And on the bottom one, on the bottom terminal, I will be executing some commands so that I can explain the infrastructure and the workflow that we have deployed. So I'm going to play the demo. Okay, the first thing that I do is to show you the Edgeless orchestration domains that we have for the demo. As you can see, there is one orchestration domain with 4 nodes. And if we inspect this orchestration domain, we can see that we have the 4 nodes, which are 3 Raspberry Pi 5, which are the home nodes, and then 1 node in the Telefonica testbed. I'm using the Edgeless CLI tool provided by Edgeless to access all this information. As you can see on the terminal on the top, you see from time to time that a lot of things happen, which are logs from the different functions. Now I'm showing you the different workflows that we are running at the moment. Well, for this demo, we are working with 3 people. and for each of these people, we have one workflow. If we inspect one of the workflows, you can see all the functions and resources that are part of this workflow. But it is better if I show you the workflow in the function repository frontend, which is a tool that allows us to define the workflows and also the functions. And here you can see the same workflow that I have included in the presentation, but with more complexity because it includes the resources also. So everything starts with the HTTP ingress resource, followed by the data passing function, the ML preprocessor, the state manager function, so on. So you can see the match between the workflow that we have defined here in the functions repository and the workflow that is running in the Edgeless cluster. In addition to that, you can see that there are several file log resources that we use for logging purposes. I'm going to skip a bit of this because I only doing the match between the workflow that you can see on the right and the workflow that you can see on the left. And now if we go to another tab, we can see the senior care application in which we can see the recent activities and anomalies of the people that we have configured for this pilot. We are working with 3 people, as I said before. Here you can see the list of activities that have been recently identified. If we go to the patients, you can see that there are 3 patients. As I said before, we have one workflow for each of these homes. And we can see also the details of these patients. And of course, if we go to the activities, we can see not only the latest activities, but the complete log of activities that have been detected. And finally, I just want to show you that the last activity that has been detected for this person is the activities outside the home. And you can see the match between what you can see on the senior care application and on the Edgeless logs. And this concludes the demo and the presentation. Do you have any questions?
Thank you very much, Fran. This is, let's say, the last presentation of the first section of this info day. If you have any question, not only for this presentation, but anyone related to Edgeless, you can do it now. Otherwise, we will continue with the second section in our presentations. So if there are no questions for Edgeless, we can go to next presentation from Dr. Ioana Capetanidou from the Information Technologies Institute. Ioana, the floor is yours.
Great, thank you very much. Let me share my screen. Okay, I hope that you can see my screen now.
Yes, we see it.
Great. Okay, hello everyone. Thank you very much for this opportunity. My name is Ioana Capetanidou. I'm a research associate from CERT, Greece, and today I'm representing the ENACT project. So ENACT stands for Adaptive Scheduling and Deployment of Data-Intensive Workloads on Energy-Efficient Edge-to-Cloud Continuum. It is a research and innovation action funded under the Data 0104 topic that brings together 17 partners from 9 different countries. The project started in 2024 and is expected to end by the end of this year. So we're currently at month 26 of the project lifetime, meaning that all the technical developments have been completed, and we're now actively validating the project advancements throughout the pilots involved. Okay, so overall, ENACT aims to support the applications throughout their entire life cycle, starting from their development to their execution, putting a particular focus on enabling their cognitive orchestration and optimizing their execution. We offer a set of mechanisms that allow users to interact with the ENACT continuum in an easy and effective manner. Starting from the application development process, we provide an application development toolkit. This assists developers in either building new applications from scratch or to customize their existing applications and prepare them to be deployed in the ENACT environment. We also offer a set of tools that allow end users to interconnect their own deployment infrastructure, meaning their clusters, the resources, their devices to the ENACT continuum without having to migrate their entire deployment to the ENACT continuum. In that regard, we also provide interfaces that support the visibility of the continuum in real time and the management of the distributed resources and applications. The deployment of applications is handled through an AI-powered orchestration engine that dynamically optimizes the workload placement across the continuum based on both application performance and energy targets. So now a few highlights on the main technical developments of the project. Regarding application development at the first stage, we have developed a software development kit. This SDK is essentially a user interface for developers that allows for automatically coding or configuring their applications prior to deployment. It is tightly integrated with ENACT's application programming model, which provides access to core libraries and also ENACT services as a set of ready-to-use templates, thus overall facilitating the development process. This SDK is also interconnected with ENACT's data and object space. This space extends the data space concept by allowing also for the sharing of code objects. So currently in ENACT, the data and object space hosts several of the self-code artifacts, such as Kubernetes manifest files, that can be directly retrieved by developers through the SDK and used upon application development. Also regarding resource provisioning, ENACT provides a zero-touch provisioning service, which fully automates the discovery and onboarding of new resources to the Edge Cloud Continuum. ENACT also provides an adaptive modeling framework, which is based on the Tosca model that captures the characteristic of the continuum, meaning both the applications, the resources, etc., in a semantically rich manner. Another ENACT offering is the Dynamic Graph Modeler. This DGM interface visualizes the continuum nodes and their interconnections in real time based on data that are collected by an ENACT monitoring engine. Through this interface, users can gain insights into the telemetry of the running application deployments, including metrics on performance, energy utilization, etc. This DGM is also integrated with the Security Risk Modeler, another tool developed within the project. This tool assesses the security posture of deployments in real time and identifies any cybersecurity threats, reporting back to the user any identified risks. And finally, zooming into the AI services of ENACT, which are actually the ones that make this continuum cognitive. So at the core of the orchestration in ENACT, we have two critical AI components, the AI forecasting models and also a reinforcement learning enabled orchestration agent. ENACT manages the entire continuum in a proactive manner, which means that we employ AI forecasting models that continuously analyze the telemetry metrics such as CPU or RAM usage and also energy consumption, and generate predictions on near future continuum state. So these predictions are then fed to a DRL-based orchestration engine, which is also enhanced with graph neural networks. Those GNN models allow also for the consideration of the relations between the continuum nodes along with the infrastructure and application metrics while we optimize the deployment of applications. All these models are continuously trained through a virtual training environment, which is an integral part of the ENACT continuum, and also assessed through an LLM-based ACCC compliance checker. This checker assesses the compliance of the AI systems with the regulations, the European regulations about AI systems in real time again. So all these tools and mechanisms have been deployed and are being evaluated across a multi-cluster infrastructure that we have created. It consists of mainly 3 clusters, each one comprising different nodes with different technical characteristics and constraints, meaning both cloud and edge environments and conditions have been emulated. So we use this infrastructure in order to validate our use cases. We consider 3 pilots in the context of the project. The first one is the distributed media and entertainment content management. So specifically, we focus on sports event broadcasting. The second pilot is the production and distribution of media content for cultural heritage and tourism sectors. For this one, we consider especially the Regata della Concha event in San Sebastian in Spain, and we enhance this event through immersive services offered for a 3D experience to end users. And finally, the third pilot is the distributed data processing for Fujitsu's Mobility Digital Twin Initiative, which is essentially a smart mobility, smart city use case. So before concluding, a few words about the project's impact.
Thank you, Joanna.
Secondly, we have the data and object space that has been recognized by the International Data Spaces Association, RADA, as an innovative solution. And finally, all the developments conducted throughout the project are being uploaded and actively maintained as an open source project in Eclipse Research Labs, which will be available also after the project conclusion. Okay, so I think that would be all from my side. If you have any questions, I'll be happy to answer them. Thank you very much for your attention. I hope I'm on time.
Thank you very much for the presentation, Joanna. It was very clear and sharp on time. I have one question myself. What about the AI Act checker? So you mentioned using LLM, if I remember correctly. But I was wondering if you tuned an LLM for that, or what else? I mean, can you provide more details about this contribution?
Okay, so yes, we have an LLM model that categorizes the AI system. So according to the regulations, it can be a high-risk system.
We lost you, Joanna. At least I lost you. Can anybody else hear Joanna?
No, we lost Joanna.
No, I think we lost her.
Let's give her a minute.
Okay. I also lost her for a bit during the last slide, by the way. So I guess it's a problem. Joanna?
Okay.
I'm sorry, we lost you right after you started answering.
Sorry. Okay, I will repeat. Okay, so yes, we have an LLM employed in the context of this AI Act compliance checker. So what this LLM does is that it categorizes the AI system based on the guidelines coming from the EU regulations on AI. So it can be either a low-risk system, a high-risk system, and based on this categorization, it has to follow certain requirements. What this LLM does is this categorization and also providing feedback to the user for any mitigation actions that need to be taken. Now, more specifically about your question on tuning this LLM, to be honest, I'm not entirely sure of the technical details because another partner is responsible for this tool. But we have already published relevant paper, which I can guide you to read if you're interested. And also the code is available in our GitHub repository. Yeah, I'm not entirely sure about the tuning.
Thank you. I'll go check the paper myself. Is there any other question for Joanna from the audience? You can just speak yourself. Speak if you want. Okay, if not, then I thank Joanna once more for her talk, and we can move to the next presentation by Spiros. He's a professor at the University of Thessaly and is representing the MLSysOps project in this info day. Thank you, Spiros. The floor is yours.
Thank you. Good morning, everyone. Joanna, you have to unshare probably so that I can share.
Yes, please, Joanna, or somebody with administrator privileges. Yes, thanks.
Sorry.
Okay. So hopefully you are seeing my slides.
Yes, it's visible.
Okay, perfect. There's also back and forth work.
Yes.
Okay. So I will try to present in a nutshell the MLSysOps project, which started 3 years ago. Now it has officially finished end of January, and we are about to have our final review. It is a multi-partner collaborative project with 4 university and research, 6 university and research organizations, and 6 industrial and SME partners. Very briefly, the goals of the project were to support autonomic system management in the continuum. The idea was to explore different aspects regarding deployment, computing, acceleration, storage, communication, etc. And the main goal of MLSysOps was to do that by using AI ML methods. However, trying to decouple the intelligence from the mechanisms. And this drove also the design, as I will explain later. So the main features of the framework, which was developed for this purpose, is it supports the deployment and management of distributed applications, meaning applications that consist of multiple independently deployable components in the form of containers, in our case. It adopts a hierarchical agent-based architecture to scale at the different layers of the continuum. It introduces flexibility by not only decoupling intelligence from the mechanisms, but also allowing intelligence to be plugged in and be used in a flexible way through 2 vehicles, plug-in policies, which in turn can include or invoke external machine learning models. And we also have the ability to feed the policies and the ML models with telemetry that is can be both system and application level. And we try also, as many other projects, to rely on mature technologies, especially for deployment, runtime, and telemetry. To give an overview of the architecture, if we look at the three levels of the continuum, so the global level, the cluster level, and the node level, we have the deployment pillar, which works top-down, basically, so we can deploy multiple containers from the continuum level. Then we decide which cluster each container is going to run, and then within the cluster on which node. On the bottom-up side, we have telemetry. We also rely on standard support, open telemetry, Prometheus. And what we do is we interpose between these two pillars an agent hierarchy, which has a continuum agent, one or more cluster agents, and one or more, of course, node agents per cluster. This is accessible through a command line interface that can be used to deploy an application, to monitor the execution, and to configure the system also at runtime, as I will explain very soon. So the continuum agent interacts with the cluster agents. The cluster agents in turn interact with the node agents, and the node agents can also twist some node level configuration knobs or mechanisms. When the application is running, we get telemetry. This is fed back into the agents per level, so that the agents can monitor the system state and can take decisions regarding deployment or even adaptation. Inside the agents, intelligence is packaged into the form of a so-called policy, which is a plugin. This can be replaced at runtime per agent per layer. And this policy can use a heuristic to process telemetry and take decisions that in turn are implemented through the mechanisms. Or policies can invoke machine learning models, which can be activated and deactivated dynamically using the system resources. We have tried to make our work reusable by the community. So there is an open source release of the core components of the framework. It includes deployment, multi-cluster orchestration, telemetry, the plugins for the policies and the mechanisms, the REST API through which one can interact with the system. And we have also a tutorial, which is also online, to explain how one can set up a system slice that is managed through MLSysOps and also run a toy application. Of course, the system is extensible, and our hope is that the community can use it to build more complex scenarios. We also had a hackathon last September in Italy at Unical. It was quite well attended. We had more than 60 people. Also, we were actually a bit surprised by the high participation. And the idea was to use the MLSysOps framework to tackle a real indicative use case to manage an application, to take decisions where to run the application depending on the current state of the system, using either heuristic or an ML. In terms of use cases, the project had two main use cases, application use cases, which had the special property of being deployed in a real environment. So this is not in the lab, it is not a simulation. We had one use case around the smart city concept for revolving around smart cameras. which was supported by UbiWare, and another application that focused on precision agriculture, supported by Augmenta, which was also acquired by CNH. And I will spend the rest of my time trying to briefly talk about these two application use cases. First of all, for the smart city use case, the challenge is to try to make the smart cameras and the image processing that runs on these cameras or next to these cameras more energy efficient. And the idea was to try to basically shut down image processing in an intelligent way so that no major detections are lost. How we did that is we used the MLSysOps framework through a special configuration for this use case with the idea to run parts of the application on the smart lamppost node, which runs the image processing filters on the camera frames. And the idea was to have not only the image processing component, but also a noise processing component, and use basically noise as a proxy to wake up image processing in time so that we don't lose any detections. And again, try to shut down completely image processing if there was no expectation of any detections anytime soon. This was tested in 2 test beds at the same time through the framework using 2 separate clusters. One cluster was used to run, deploy and run and adapt the application in the private testbed of UbiWare. And the other cluster was to use public smart cameras which actually provided video footage of a real street in the city. The results were pretty satisfactory. So indeed, through ML, we managed to save up to 40% with an average of 20% of energy on the smart lamppost node, thanks to completely shutting down image processing without missing out too many object detections compared to ground truth. And of course, this is highly, let's say, location sensitive and dependent. If you are in a street that has occasionally very low traffic, this indeed will save you a lot of energy without missing out any important events. But if you are in a busy street, such as in the public testbed, then you have almost always some traffic going on. So the machine learning will not help, but it will also not lead to any false, any bad decisions. In the second use case, the idea was to improve the so-called spot spraying in the field. The idea is that there is a device on the tractor that scans the field in front of the tractor. It runs image processing to detect weeds with high accuracy, and the location of the weeds is used to control the sprayer so that you only spot spray on the right locations where there are weeds, whereas avoid spraying and stop the sprayers on the locations that don't have any weeds. The problem is that the camera system on the tractor, it can get blinded by the sun or reflections. And in this case, the system enters a so-called safe mode where the whole spraying system is activated in order not to miss out on any weeds. Of course, this leads to waste of herbicide, increased environmental impact. And the idea was to use a drone in tandem with the tractor to provide a complementary view and weed detection information that could improve the situation and basically reduce the amount of time the tractor is on the safe mode. And the challenge was also to reduce the useless flying time of the drone. So, of course, in theory, you could have the drone flying all the time, but this also has resource constraints. The battery runs out pretty quickly. So the idea is to really use it only when necessary. So again, we used machine learning to drive the deployment of the image processing logic on the nodes and to also engage and disengage dynamically the drone based on predictions about the safe mode operation of the tractor. The results were again quite satisfactory. So compared to the default case, where with red you can see the region of the field where the tractor was able to detect weeds and perform spot spraying. With black, you see the area where the tractor was blinded and would blindly spray the whole time. And with MLSysOps, we see that these black regions indeed became much more informative, and the tractor could maintain the precision spraying mode. Also, machine learning was able to eliminate useless flight of the drone by predicting basically the regions where the tractor would enter safe mode and control the drone to take off in advance, and then also be disengaged when no value added would be there. It is important to stress that the drone was completely automatically controlled in a control loop, so there was no manual intervention. Of course, we had a pilot standby for safety reasons. There are many more results produced in the project. We had ML AI being used to take decisions for task management in the continuum, job scheduling in data centers, intelligent storage management, optimized ML workload execution on resource-constrained nodes with FPGAs, acceleration at the edge, deployment at the far edge, where you cannot run proper containers and you have very resource-constrained nodes. So special work was done to support such nodes as part of the continuum as well. Lots of work regarding 5G networking and also anomaly detection. So we have produced many papers. They are all open access, and also several data sets and ML models that are openly available. So thank you. And please check out our website. All public deliverables are there. The papers are there. The framework has been open sourced through GitHub, and all our work is also in Zenodo. The ML models, the data sets, and some of the papers, if not on ArcSIF or other open repositories. Thank you very much.
Thank you very much, Spiros, for the presentation. It's very an impressive amount of work. I praise in particular the engagement of the community via the hackathon. It's really an amazing result, 60 participants.
Yes,
We have learned that it is very difficult to engage the community, so
Actually, we were very surprised when we saw the registrations coming in, because initially we planned for 20 people. You know how it is. We were definitely not expecting 60, and it was a huge amount of work. And I take the opportunity to especially thank the University of Calabria and Raffaele Gravina for organizing and managing this crowd because scale is really, we had to set up many more slices than expected because each team had to work on an independent system slice to avoid side effects. So we had to maintain 6 or 7 separate deployments at the same time. It was a challenge, but it was also very huge fun, I think.
I know that there are sometimes specific calls for projects focusing on open source engagement, but in this area, I think that many, if not all of the projects have some strong open source side to them. So I'm just thinking aloud if it would make sense for the European Commission to also set up some structure for all the projects in this unit to run these events in a more structured manner.
Indeed. I think we also spend a lot of time and resources, and I think it was the case for every project in these calls, to try to do the same thing. So basically, everyone is more or less kind of reinventing the wheel with a slightly different way, but indeed it would help a lot. And I think this would be a very good role for the CSA projects, for example. I mean, not just organize webinars, etc., but really put a structure in terms of open source projects, hackathon. Indeed, this would be a very good idea, Claudio. I fully agree.
Thanks. Does anybody want to comment on this point, or does anybody have any question in general for Spiros? Okay, if not, thank you again, Spiros, for the presentation. And we can move to our next speaker, Professor Adlen Sentini from Eurecom, who is representing the project AC3. The floor is yours, and you should be able to share your screen now.
Okay, good morning, everyone. And first, thanks for the invitation, for giving us the opportunity to present the activity of the project. So it's my pleasure as a technical manager of the project to present the achievement of the AC3 project, which is about agile and cognitive cloud edge continuum management. So quickly, the project has been founded in the call CL4 data 2022 data 0102. The project is about closing, so we have the final review by July 2026. So the consortium is composed of key industrial partner in the cloud edge continuum, IBM, Ionos, and Arsys. These two are the cloud provider, and of course Red Hat, which is well known as industrial for providing the technology for the cloud edge continuum. We have SMEs coming from Greece, Spain, Finland, and Ireland, and academic partner in the project. And I'm the technical manager, and Christos Verikoukis is the coordinator of project from Easy Athena, Greece. So what is AC3? AC3 goal is to design, develop, and evaluate the cloud edge continuum computing manager. So the objective is to provide a tool and a framework that allow a developer to interact with the cloud edge continuum in order to create and deploy application over the cloud edge continuum, and then the service and the system and the cloud edge continuum manager take over by ensuring that everything is, the application is supporting, is getting the needed resources from computing, but also from networking, and combine everything to ensure SLA. And all the applications that are supported by the project are based on microservice and pod deployment, cloud native. And we are supporting in the project migration, scaling, energy saving, and so on in order to ensure the SLA of the application, but also provide the application developer way to update its SLA on the fly. For instance, to add more computing resources if it deemed appropriate, but also interact with the networking. So the network interaction of networks are based on SD-WAN technology. So we are building overlay, which means that we are not stuck to any network operator. Everything is managed from the overlay perspective. Also, the project aims to add the application developer the possibility to integrate data management procedure if it is about adding sensors to the application or a huge amount of data. So we are not touching the infrastructure, but we are relying on federation. So this federation is relying on a well-known standard from IEEE. So we are supporting 3 use cases that I will come back later on. So this is the vision that we have for the project. So we have like an infrastructure that is composed of far edge, edge node here. So edge node and central cloud, and we deploy an application over all this continuum. And for this kind, we are providing in the project this Cloud Edge Continuum Manager that support an application developer that providing a graphical user interface and friendly interface in order to design its application and connect all the necessary data source to the application and the deployed. Then this Cloud Edge Continuum will take over by supporting, AI and XAI tools in order to ensure that the life cycle of the application is achieving what the application developer has specified in SLA. So in terms of output of the project, so we defined the architecture of the Cloud Edge Continuum Manager, and we developed different components. So for instance, this ontology and semantic reasoner that allow the application developer to create and design the application in order to be ready to be deployed over the Cloud Edge Continuum. We have designed data catalogs that are following the Gaia X approach and service catalog. It's act like a place for the application developer in order to design its application and deploy it. And of course, we have some kind of KPI collection and exposure. So then we have the application lifecycle manager deployment that is running the ML and AI models in order to ensure that everything is working well. So it is in charge of doing like a closed control loop over the network, look into monitoring information and everything related to observability, and take a decision. So these decisions are mainly to scale the application, migrate the application over the continuum, and so on. And we have the federation that allow to discover resources. So this has been done in order to allow any one that has, for instance, edge computing and want to enter a federation to expose the resources, and the resources will be used by this Cloud Edge Continuum Manager to run and deploy application over of it. And of course, we have external data source. So we are supporting hot and cold, using what we call data connector and data application add-ons. So through the marketplace, which allow the application developer to not bother itself about how to connect the sensors and the data, but everything is done by this Cloud Edge Continuum Manager. So for the project, we are supporting 3 use cases. The first one is IoT and data. So this use case proposes an IoT-based smart sensing and monitoring framework that leverage Edge AI within the Cloud Edge Continuum. So it improves infrastructure monitoring and management from smart home to large-scale smart grid, independently of the underlying sensing and communication technology. So this is the global architecture. So we have sensor deployed over a building, and we allow an application developer to create its application and deploy it and connect to the data source, which are here. So these data sources are run as microservice over the edge, and some components are run over the cloud. So the components run over the cloud are centralized at Ionos Cloud, and here this edge is deployed at the premise of one partner in Barcelona, and the application developer can connect the sensor and create the application. The second one is smart monitoring system using UAV. So here we are using drone in order to supervise an area. And here we are taking the advantage of telco cloud, where the drone are connected through 5G network, and the drone capture the video analyze the video and send the analysis to an edge node. And this edge node extract meaningful information and forward it to the cloud. And the cloud expose the object detection. Here we are using YOLO. And the cloud node is centralized at EONOS premises. And the analysis of the video that is captured by drone are in the scenario, one time is already deployed on the drone. If the drone has no capability to run it, we migrate toward the edge. For this, we are having a drone that on board an NVIDIA Jetson Oran in order to do the analysis. And if the drone cannot do the analysis for any reason, like the battery is going low, then we migrate in lifetime this from the far edge, which is located at the telco cloud, to the edge node, which is located also at the operator premises in order to the analysis. And the last use case, which is like multidisciplinary, which is about distributed and scalable processing of astronomical data. So here we are working with the University of Madrid, which has a lot of data that are captured from their astronomic system. And they have issue in order to run this data and to visualize this data, using only one cluster. Here the objective is to have many clusters that are interconnected with the cloud in order to visualize this. So let me show you a small demo because the project are about ending. So the first demo here is about the marketplace and how a user interact with the Cloud Edge Manager. So the user have this interface. Here there are some different profiles which are corresponding to the use case, but the user can add a data node. So here we will show the data management. So for instance, this is based on Pivo. Pivo, for those who are very familiar, is the one which is supported by GaiaX. And we provide the application developer the possibility to register its data sources. So here, for instance, we can add a data source. So this data source, we put it, the name is data set, but this is the jargon of Pivo. It's not related to any called data set, but it is the data where we can collect on and interact with to get the different resources. So here, the application developer can register its data and then can specify how to consume this data using the Pivo system that we are providing for the project and the type of microservice that need to be run. Then here we have the example of the data source that we have in Barcelona. So this is where we have the data source and the application. And we have also a service offering where the application developer does not need to provide any image. The image are already here in the marketplace. So he just need to compose with this the different images that we have here in this Pivo system. So we have a data catalog and a service catalog. This is the service catalog. And it can, for instance, create an application. So for instance, here we have already an application. So it can update it, add in the interfaces and the sources. And what we generate here is we can call the different source name that we have created. So the application developer just add it to the application profile that is created. And then he has the possibility also to add this in specific area or interact with Pivo, because this interaction with Pivo allow to already have a preloaded, I would say, microservice to manage the data. So this is all for the marketplace. Now for the second one, so this is representing the one of from University Carlos in Madrid about the physical astronomical data, that how we operate them.
if we are supposed to listen the audio, there is no audio.
Sorry, there is no audio.
No.
Okay. I think, sorry about that. So this demo show how we update upload the data that is coming from the astronaut, because they have hardware to collect this data. So then this data is uploaded into Pivo, and then this data, and then we will show. So all the data will be forwarded. Sorry, but there is a sound on it, so I'm sorry about that. But this demo has got a demo award in one of those to overcome the limit of one cluster to handling this high amount of data. But here that we can, the application developer, just have this data uploaded into the AC3 system, and in this will be in the background using the best cluster to handle all this high amount of data. So this is all from my side. Thank you for your attention, and if you want to have any question.
Thank you very much, Adrian, for the presentation. I would have a quick question.
Yeah, go ahead.
Regarding the heterogeneous devices, because something which has created a lot of difficulties in Edgeless for us has been the migration from different types of nodes, because one node might have a different operating system, a hardware architecture. How do you handle that? You showed us there is a marketplace. Does the marketplace include all the binaries for the different or images for the different architectures?
Yes, excellent question, Claudio. I think what we did, because as you mentioned, for instance, Edge node, when we run the application on Edge node, the Edge node run Intel. Why? When we go far edge for NVIDIA is ARM. So what we done, I mean, in the marketplace, as you mentioned, we have a different type of image. So we have the image that run on ARMS and the image that runs on Intel. So then this Cloud Edge Continuum Manager has the intelligence when it comes to migrate from ARM to Intel is to use the right image. But of course, if we have to run, to do this, which means that the migration will be not hot, but it will be cold. So we stop the pod, for instance, on the ARM, and we run the pod on the Intel. But the system has been made where this small downtime is not very affecting the all the overall experience of the user, because all the pod has the same DNS name inside our system, which means when the user is redirected, it's redirected by DNS name, which means that it's somehow transparent in terms of request.
Okay, I understand. Thank you. Well, it makes a lot of sense. I also mentioned because in Edgeless we discussed it, but we did not push that. Unfortunately, we didn't have time and resources to push it further. We discussed the possibility to have the source code for an application and then to compile it just in time for the specific target architecture. That would be very cool. I don't know if there is already technology for that.
No. I mean, for us, what we did is when the application developer, for instance, here requests the deployment, so our management plan push the two image if there is like a possibility of migration between Intel and ARM. If there is only ARM, there is no need to push the two image. So we have like an intelligence here within this orchestrator that knows that for this scenario, perhaps there is a need to two image. So then it's upload the two image into the system.
sounds very reasonable. Thanks.
Yeah.
Does anybody have any question for
Yeah.
Adrian? Yeah.
I have a small question related to these aspects. How did in your application did you have the problem of migrating the states? I mean, I can understand the problem of the container, but if there's an history that matters, how do you migrate the state of the application?
Very good. I mean, we have two types. I mean, we have migration of stateless and stateful. So what it was explaining to Claudio is the stateless one, because with the stateless we can have different image. For the stateful, we didn't solve the problem of different platform, so we can do the stateful, for instance, using a technology that Red Hat has. I don't remember exactly, but we have this in our deliverable. Or if you can send me an email, I will give you the exact technology.
Okay, thank you.
You're welcome.
Okay, thanks. So in the interest of time, I would move immediately to our next speaker, who is Francesca, by the way. So please, please keep the floor, and thank you for your presentation.
Okay, sorry. Sorry for interrupting. We had a discussion earlier by mail. We can change the sequence between MYRTUS and CODECO.
Yeah,
I
no
do not
problem.
know if it is the case.
I would appreciate, because I'm really sorry, but I have another meeting at 1 that I coordinate, okay, and I cannot cancel it, okay? So
thank you both.
Thank you, Spiros. Let me share, and Francisca, share the screen. Okay. Okay, I think you are seeing the presentation, right?
Yep.
Okay, so hi everybody, and first of all, Spiros and everybody, thank you for having us here. So you already know a little bit about CODECO. In terms of orchestration, today we heard a lot of things that are quite similar in a sense in terms of orchestration, so migration aspects and so on. I would start by the aspect that I think is a differentiator, so in comparison to other proposals, which is, so there are others, of course, because we are speaking about Edgeless, which is serverless. So in our case, CODECO is an orchestration framework similar to the others that have been presented here. As you know, we started at the same time. We are going to close end of March. The final event is being planned to be in Munich, standalone, so you will get also an invitation in Fortis. And so what we have been trying to do in terms of orchestration was to bring, so we wanted to focus on decentralization, so let's say the architectures that problems that we have today on the internet, and therefore we decided to focus more on the application as a whole. So let's say application where the architecture is based on microservices. So these are the so-called workloads. Of course, the microservices are pieces that need to communicate together, and that's where we focus. So we wanted not just to work on the migration, but actually to ensure that the whole, let's say, application graph would be kept with the same conditions. So the application to us, therefore, is similar to most of you, is a black box. We don't see it, we cannot do anything. So if it was, let's say, deployed to run on a GPU, then it has to run on a GPU. If it was deployed to run on ARM, then that's the case, okay? But normally, so what we say is that there is an infrastructure that is heterogeneous from far edge to cloud, and our application should be able to be deployed there and should also be able to be migrated. And migrated here means that we consider that the infrastructure is mobile and we need a high degree of portability. So before I jump into the architecture, I will just tell you what we did so far and what you can already use. So basically, the core of CODECO is called CODECO now. It's an Eclipse set of tools. Right now, we are migrating the code from the Eclipse Research Lab repository. So there you have what is CODECO that I will present you next, but you also have a synthetic data generator that generates data based on the observability of CODECO of the infrastructure. So let's say data layer, computational layer, and network layer. You have also applications that were developed on the 6 use cases that CODECO has. So across smart cities, energy, smart buildings, so CDNs, I believe, and manufacturing. So that use case is with us. You have also an interesting experimentation platform. So it's, I wouldn't say it's not really just an emulator, but it's basically an automation of the full pipeline of experiments that we want to do. So we can run different applications. We have also created dummy applications, but you can also use regular applications available, your applications, and then do a deployment together with CODECO of a full experiment, compare it to other approaches, and get the results. So this is what CODEF does. And of course, if you go to YouTube, you will see some demos of our use cases. And so currently, let's say we are on the final stage. So CODECO has 2 modes of operation. As said, it's a set of tools that does orchestration of applications across a decentralized IoT to edge to cloud continuum. In that context, the core operational aspect relates with Kubernetes. And what we are doing is bringing the application deployment to multi-provider federated environment. So that is the core of CODECO. The approach itself, the way CODECO looks into the application is, as said, we say, okay, there is an infrastructure that the application needs and that requires data, computational, and the network, let's say, orchestration. And in our case, we do it at the same time. So we don't do it layered, we do it at the same time. So for that, we bring to the architecture a number of, let's say, we bring observability and a number of metrics. So you have on this slide on the right-hand side, the categories of metrics that we collect. For user behavior, I would say this is just in concept. We just use user preferences, for instance, QoS or security, so or some compliance aspects, but we are not yet playing with, for instance, volume of visits to a node, etc. We have a use case with CDN where this can be done based on the ETSI MEC API, and there will be a final demo about this, but basically this is not fully integrated in CODECO. All the other features are. And so what kind of components do we have? So this is CODECO, I would say. So CODECO is a set of 5 components, so what we call Eclipse CODECO. And the user is a developer or a manager of the application across the continuum. And when the user wants to deploy the application, basically the first step is, of course, to install CODECO. And this means using this component that you see on top, the ACM, so automated configuration management and security. So basically that's what the user sees. Okay, it's an operator, and then all the other components are deployed automatically on the right places. I will explain this in a minute. So this is a control plane solution. So this means that all the components that you see here, they belong together with the control plane of Kubernetes, plus the observability, which I would say is also on the service plane. So it's control plane, but we are actually installing some components or some pods that do observability on the so-called Kubernetes worker nodes. So in more detail, so you have information about the architecture in different deliverables, also in papers. There is a more recent paper that explains the federated concept. Here, what you see, these components, they can be deployed in different environments. They are on the control plane, so this is for Kubernetes lingo. This is the so-called control plane node or master node or master nodes, but it could also be installed anywhere else. In terms of software, this means that it is prepared to run on the edge. So for instance, in our case, we have a use case in manufacturing where we run it in ARM, with K3S, but it can also be run on the cloud, edge to cloud. So the different components, so I'm going to fix more on this because I think it's more important, maybe a bit more confusing given time. So what you have here is an example on where CODECO and how it is deployed in a multi-provider federated cluster environment. And what you have here, so basically we of course use a solution that is available. As you know, Red Hat is also with us. Therefore, CODECO is using for the multi-cluster management, the open cluster management project. And then what we did was that we improved that on two aspects. So we made it more decentralized. So in the sense that normally there is, let's say, a control plane, a hub cluster, which basically supports, let's say, the registration of other clusters across the continuum. So this is what you have here with managed cluster 1 and 2, okay? And what we did was we worked so that the communication between managed clusters would be so horizontal. So this means that we don't always need, so let's suppose there is the need for a migration of an application or to get more resources to do auto-scaling or load balancing. We don't need to go to the hub to do that. So basically the hub is used just to do the setup of CODECO and also of the environment where the application should run. And that environment is also something that we do that we call neighborhood. It's basically a concept of a community. And so let's suppose we have an application to be deployed and we have a large space, because now we are on a space of federated clusters with thousands of nodes, hundreds of clusters. This means that, of course, CODECO does not need to check the resources and the availability of all clusters. It actually, so we have a plugin that we created that does sort of a sweep across the problem space and then selects clusters that are more relevant to the application. And by more relevant, it means that when the developer decided to deploy the application, the developer also selected some reasons that were more important for the performance of the application. For instance, greenness. I want my application to be deployed and to consume the least energy possible in this deployment. Or I want my application to be deployed in a resilient environment. So these are things that are defined in the CODECO application model that I'll show in a model. So a semantic abstraction of the application that is managed by this ACM component and which is visible to all CODECO components. So this means also that in terms of, so here, for instance, on this example, there is a user defines the application based on a GUI or on a YAML file, which is this CODECO application model. This is then worked by ACM, which is this operator, and ACM passes it to all the other components. The CODECO components, they are installed on, on what we define as neighborhood. So this definition could be static. We can say first 10 clusters available. But in our case, it is also based on the value, so on a weight that we can compute, for instance, for greenness of the cluster or for resilience of the cluster, or how much, so what is the bounded latency that in average the cluster can give. And then inside the cluster, of course, CODECO selects the best nodes, let's say, and if necessary, let's say migrates. This migration can occur within, as you see here, within this neighborhood, so from one cluster to the other. It can also occur towards other clusters. So what we have implemented, and not just concept, is basically what is available here. So it means that the migration that we are doing, once the neighborhood is defined with multiple clusters, that's where we will play with the resources. But in concept, there is a deliverable which explains you also how we can work with this. Okay, so in terms of, as I said, one key aspect in CODECO is observability, but also how do we weight, let's say, the nodes, how do we bring this context awareness together to the machinery of CODECO and Kubernetes. So as I said, we don't do this by layers. We don't say there is a graph and then we take a look into the node resources and into the network. We actually do it together. So we have a scheduler, which is under this component, SWM, that relies on ILP solvability and basically grabs this CODECO application model, checks what are the resources, okay, that were collected based on the infrastructure. And these resources can be CPU, memory, all this is also defined in the CODECO application model by the user, and then does a decision on where to place the microservices, so the workloads of the application. Now, the scheduler does the placement, but we also use PDLC, which is another component that is AI-driven, uses multi-agent reinforced learning to generate recommendations. Okay, so it learns about, okay, the application was deployed and migrated, but maybe 5 minutes after one of the pods had to be migrated back. And to avoid ping-pong scenarios and these kind of things, these recommendations are also sent to the scheduler as regular costs. So this means that the scheduler weights also these recommendations, but does not necessarily do a placement just based on the recommendations. So I'm going to jump a little bit because I think we are running out of time. So you have here an example of the semantic model for the application, this CODECO application model. So what you see in Lila means it's the spec, okay, so what we specify, we have more. There is a deliverable that has all this. And in our code in Eclipse, you also have a list of metrics that you can use, plus they can be extended. So what you see here, for instance, QoS class, security class, some of them are ready to be used, not necessarily used. Up, energy limit, failure, etc. These are things that the user defines and says, okay, I want my application to run in an environment where the link fails at most 2 times, something like this. And then basically this specification is then passed to all the other components, and the scheduler uses this to do a decision based on what was observed on where to deploy the application. What you see in pink is basically information that the components of CODECO give back via ACM to the user. Okay, so to try to also close, CODECO has said itself operationally right now is ready to run on the edge. This means far edge in ARM. It can also run across. So for instance, we have a use case together with Göttingen University where actually CODECO is running on the cloud. So there is a part on the edge and a part on the cloud. So this depends a little bit on the scenario, but right now, so what you see here is basically examples of where the different components could be deployed. Not all components are also mandatory, so I would say that normally, for instance, we need ACM, which is the operator, we need the scheduler, which is inside SWM, we need observability. If you want to have network observability, we need NetMA. Okay, so these 3 would be minimum, I would say. But if you don't want network observability, then you can also use ACM together with a regular Kubernetes vanilla scheduler, for instance, and even play a little bit with other things. Okay, so on our final work, okay, and what we are doing now, we are also comparing CODECO to other approaches that are federated, and so you have some information on this paper, okay, or right now is a preprint, but it's under submission. And I would just close by calling the attention. So we have, as you know, possibly next Friday a standardization meeting where some of you will also be presenting. So there we would welcome all of you. So what we're trying to do is to do a discussion more focused now on the standardization, let's say assets that were passed to standardization, and discuss how we all see these, okay, and possibly also try to engage in something together to the future, maybe an IETF side meeting in Vienna or something like that. There are also some awards, so we are still running a program until next week, okay? So I don't know if you know about this, but I leave you with this information and I thank you for your time.
Thank you very much, Ruth. So in the interest of time, I would skip the Q&A session. So if anybody has any question, please get in touch directly with Ruth via email. You can easily find that, I guess. And I would leave the floor to Francesca. Thank you very much, Ruth, for the presentation. You are muted, Francesca.
I was checking that. Can you see the presentation?
We can see it in editing mode, however. Now it's presentation mode.
Can you see in presentation mode, right?
Yeah, from the presenter view.
Okay, perfect. The presentation or the
No, we're looking for the with the wrong view, I guess. So this is the view you should have. We are watching it.
I don't know how to share the second screen.
You could present it with the one on the button on the left of the presentation.
Condividi.
Otherwise, you can just maximize this. It will be just fine.
Okay.
You should remove the notes.
Maybe you should see
the desktop.
Now?
The desktop. Oh, no, that's fine. Great.
Okay. So, but I don't see the presentation anymore. Okay. Fine. Good morning, everyone. My name is Francesca Palumbo. I'm associate professor at the University of Cagliari in Italy, and I'm the scientific coordinator of the MYRTUS project. MYRTUS stands for Multi-Layer 360-Degree Dynamic Orchestration and Interoperable Design Environment for Compute Continuum Systems, and it's a consortium. It's an Horizon Europe project started in January 2024, and the consortium is composed of 14 different countries that we grab together. Fundamentally, we have different expertise, going from low-level architecture design to software management strategies. The projects aim to provide solutions for the efficient computing. I don't know whether you are seeing the presentation, to be honest.
We are on the first slide.
Oh, gosh. Okay.
Okay, now it's moving back and forth. Ambition in a nutshell.
Okay. And the goal of our project is to provide efficient solutions for computing continuum management, leveraging AI strategies. Three different ingredients are composing our project. The first one is the definition of a reference computing continuum infrastructure, which peculiarity is the fact that it's composed by heterogeneous resources to be managed through these, to be orchestrated and managed by MYRTO, which is an AI-powered cognitive engine that represent the core of the project and is capable of managing both workload and customization and resource customization at runtime. To deal with the complexity of the design of such an environment, we are also defining a design and programming environment. It's a unified end-to-end environment covering all aspects that going from high-level modeling down to deployment. All of these three main ingredients and main technical goals are to be assessed or in the process to be assessed, I would say at the moment, into two use cases, which I will not cover today because I'm going to focus mainly on the technical, on the key technical pillar. The two use cases are one on mobility and the other one on healthcare. So the first challenge that we are facing is a widely known one, is the cloud edge dichotomy, and we are all used to hear about pros and cons of centralized cloud-based solution and decentralized edge ones. The computing continuum paradigm, as we all know, has emerged to overcome these issues and the limitation of the individual approaches. But despite all the presentations that the nice presentations that we have seen today, I think we can agree on the fact that there are no widely accepted solution, and that all the frameworks that are around are mostly fragmented and proprietary. What we are doing in MYRTUS is to try to define these this reference computing continuum infrastructure, following the guidelines of the standardization initiatives that is called EUCHE. In MYRTUS, what we are doing is defining this infrastructure that is composed by an heterogeneity of computing resources that spans from edge to cloud, that include also application specific at the edge, application specific accelerator. So all the nodes that we are considering are highly heterogeneous and highly customizable. All of these nodes are brought together, exploiting virtualization techniques, among which I can mention that we are using LICO, that is from Aruba Cube. The goal is to enable the seamless orchestration, of the workloads across all these resources. Here is with this slide, I wanted to summarize the fact that we are trying, as I said, to adhere to the building blocks that have been defined by the EUCHE standardization initiatives, and I want to mention the fact that for example, for resource management and orchestration, we are using in all layers Kubernetes and LICO, so from the cloud to the edge, and virtualization technologies like Docker to establish this continuum of resources. The second technical challenge that we are facing is apart from the creation of this continuity of computing resources, also the orchestration of these resources. And again, the dichotomy that we have seen at the infrastructure level is also there at the management level. For example, LICO, that is the technology that I mentioned before, provided by Aruba Cube, before MYRTUS was capable of really seamlessly bridging together different cluster of resources in different cloud regions, but never stretched till the edge, where heterogeneity makes difficult to adopt it. What is the effect of this limitation is the fact that there are severe limitation of the optimization potential that you can have at runtime if you are considering the different layers as isolated silo. What we discovered when we started MYRTUS is the fact that algorithms for workload optimization are certainly there, but they struggle in coping with the heterogeneity, and they struggle in really offering cross-layer management of the resources. And here is where we are trying to advance the field. Indeed, our goal is to exploit artificial intelligence for orchestration purposes, trying to realize the self-adaptation loop that is typical of autonomic system. The orchestration and reconfiguration of the system and the workloads running on top of it, it's triggered in our case not only by latency related matters that are mostly the triggers that is mostly seen around, but also by energy efficiency, by energy efficiency and security guarantees. we do that by deploying MYRTO. That is our orchestration agents. The continuous monitoring and observation that are enabled at the infrastructure level allow MYRTO to make informed decision regarding resource allocation, task scheduling, and system reconfiguration. So these MYRTO agents that you see here not only allows to redistribute at runtime the different workloads from one node to another, even among different layers, but also to configure the different resources at the edge. MYRTO is used both at deployment time. In that case, it also leverages some information that comes from the MYRTUS design and programming environment and combine those information with those that are stored in the distributed knowledge base resource registry, but also at runtime. And the triggers at runtime may come either from the application, so come from the users, or from condition that can happen at the node level. So, for example, failure of some particular node. The goal, as I said, is to enable this continuous optimization at runtime. To favor the uptake of our solution and allow the portability of MYRTO technologies, we are leveraging standard technologies that I already heard in the other presentations. For example, to orchestrate the deployment of the workloads, our deployer uses Kubernetes and LICO, and makes use of Docker images for container definition. Moreover, we are adopting, and I think I heard it also in other presentation, we are adopting the Tosca language to provide MYRTO with a model-based description of the infrastructure and the services, and to annotate the characteristics such as the requirements or the operational policies to be taken into consideration. Last but not least, as I said at the beginning, to handle complexity, we are also defining a design and programming environment. Indeed, one of the biggest problem in computing continuum infrastructure is the fact that there are many instruments available to program and deploy solutions either in the cloud or in the edge, but these solutions converge with each other. So in the context of continuum computing, there's a clear need and there's a clear gap for a design and programming environment capable of cross-platform support capability. And this is where we are trying to invest our effort in. We are creating this design environment that go from the initial application level specification down to software components and accelerator bitstream definition. And this design environment, apart from spanning, as I said, from end-to-end, so from definition down to deployment, has also some important key ingredients that are security and privacy by design, support for deployment and runtime orchestration, and cross-platform compilation to avoid vendor lock-in. Even in the design and programming environment, to facilitate the easy uptake of our solution, we leverage industry and academia backend frameworks, again, Tosca to describe the application, but also MLIR for cross-compilation purposes. The DP is quite complex. It's composed of three different steps. In the first one, we analyze the application, we prepare the Tosca model for deployment, and we also define the attack defense tree that is useful for risk analysis, and that is used in the second step of our DP for defining and automating the countermeasure definition. In this second step, is called model to implementation, because we take the initial Tosca model. We are capable of doing automatic code generation and countermeasure synthesis and countermeasure synthesis. Having available the models, the C++ models, then everything is digested by the third step of the framework, where we leverage MLIR, an MLIR-based environment to create both to compile both the deployable microservices and to define the specification of the hardware accelerators. The goal, as I said at the beginning, is to create a unified environment for users to be able to deploy complex application in heterogeneous cloud edge computing infrastructure. This concludes mostly my presentation. It was just an overview of the key main ingredients of the project. I leave you with some links. In particular, we have a Zenodo community where you can find all the publications and also the deliverables of the project. Thank you for your attention, and also for the invitation to this very nice event.
Thank you very much, Francesca, for the very interesting presentation. Is there any quick question before we close the info day, which has been a bit late, sorry. Tony, who moderated the first half of the info day, has been much better than myself in moderation. I got a session which started earlier, and I have a session which ends late, but it is entirely my fault. So, okay, if there's no burning question, I would thank everyone for being here. Yes, Piros?
Yeah. So thanks, Francesca. In one of the slides, I noticed that you target also FPGA-based nodes. Can you tell more about the targeting, the focus targeting of FPGAs? For example, for ML models, things.
Actually, we have. It's a great question because it's my field. Thank you. And we are working on different type of FPGA, FPGA nodes. We have a flow for it's called ONNX to MDC. There's a paper on Zenodo for that, and starting from ONNX model, we are able to infer CNN models on the processing logic of the FPGA. And everything can be orchestrated within the MYRTUS environment, because on the processing system side, we have this software stack that comprises Kubernetes, lightweight version of Kubernetes and Lico to orchestrate containers that can do ML. But it's not the only type of accelerators. There are also accelerators for other type of applications. We are using Artico framework from UPM, and also a CGRA reconfigurable RISC-V implemented on FPGA, again from UPM. So there are very different types of FPGA nodes there that can be exploited. The good thing is that all of them interface with the MYRTU cognitive engine with the same software stack that allow us to connect the nodes.
Okay, thanks a lot, Francisca.
Thank you for the insightful final discussion. So I thank all the speakers of the Info Day, and I think this takes us to the conclusion. I thank you also the attendees for bearing with us until now, and I wish you a nice continuation of your working day and week.
Thank you very much again. Bye.
Goodbye, everyone.
Thanks for having us, Claudio. Thanks a lot.
Thank you for coming.
Bye bye, everyone.
Bye bye.